Okay, well, hello everybody. I don't have any tool or software to sell, but I will speak about physics a bit, and I will mainly speak about sources that we did not discuss much. We spoke a lot yesterday about gamma ray burst. So in the next 15 minutes or so, I will speak about microquasars, which are the X-ray binaries, so accreting binaries, and I will tell you how these sources can be very transient in many different ways. So you have various type of binaries. You have the detached binaries. So these ones are not very interesting for us because they don't make many high energy phenomena. You have the semi-detached binary, and these are the ones that will interest us. So this is the scheme I will describe, and this is the kind of sources that you can have. So you have mainly one normal star which lives its normal life and close to a compact object, and you have matter accreted from the normal star to the compact object, accreted through an accretion disk, and you have also jets coming out of it, and so both the disk and the jet can make transient high energy phenomena. And you have the contact binary, which I will not discuss here, which is more important in the context of the evolution of X-ray binaries. For instance, up to the merging when it emits gravitational waves. So this is exactly what we deal with when we look at the common envelope phase during the evolution of the binary. So I will focus on the semi-detached binary, and this is the Roche geometry, where you have the center of mass here, you have the two objects here. This one is the most massive of the two. So you have the L1 point, which is exactly the point where the matter from the star, if I look at this drawing here, you have the matter from the star going through L1 point and then accreted, forming an accretion disk, and then accreted on the compact object. And the other one points, the other Lagrange points are not important for us. This is seen from the top. If you see it from the side, you see something like this in 3D. So the Roche geometry is really very important in this case because it describes what will happen in these sources. So for the drawing you have here on the right, the star is filling its Roche lobe, so it's filling everything here. So you see that it doesn't have a spherical shape; it has like a different shape, which is a bit oblong. And so the matter is coming out. It stays within the border here, passing through L1 and then accreted. So this describes the shape, the sources, and so you have this drawing here on the right, but you have also some sources for which mainly for the high mass X-ray binaries that we'll see later. The star here doesn't fill the Roche lobe, and so matter cannot be accreted, forming an accretion disk, but it's just the wind of the star, stellar wind, that will be accreted by the compact object. So you have different objects which are really related to the physics and mainly to the masses of the two objects, the mass ratio, and also the orbital separation. And so the first microquasar recognized as so was the source SS433 in the 70s and the end of 70s. So you see here, so this is a radio VLA image that you see of all the environment. So it's a very big side. And you see here the source, so superimposed to the central source. I've put a drawing. You don't see this like this in the real world. So there is a black hole here between 5 and 9 solar masses. You have a binary system, and you have the jet here. This is the jet seen in Chandra with the Chandra satellite. And you see also the result of the jet on the surrounding medium, because here you can see that there is an interaction between the source and a supernova remnant, which is W50, and you see the jet, which is so ejected from the central source, and which is impinging on the surrounding medium, and so creating the nice shape that you see here. So the binary system is made of a star which is nearly between 8 and 15 solar masses. Black hole is between 5 and 9 solar masses. Symmetrical jets, relativistic particles with 26% of the velocity of the light. So relativistic particle. You even see some not only electrons, but also baryons ejected in these jets, and so a lot of energy involved in this object. Well, this is the schematic view of this object when you try to model how it works. So what's interesting here, what gives the shape of this supernova remnant, which has been modeled by the jet impinging on the shell, is mainly the precession of the jet. So the jet opting angle is precessing, and so it gives this view that you could see on the previous slide. Okay, so energy phenomena. This was a model made to constrain all the geometrical parameters of the system that we could see with the new star data. This is how an accretion disk is mainly working. So you have this Keplerian disk accreting inflow. You have some magnetic field. Different models can explain how or describe how the matter accreted is then ejected thanks to the magnetic field. I will not spend too much time on this, but I wanted to only to remind you that we have galactic binaries hosting many different compact objects. So this is the case of a white dwarf. So you have the companion star, the white dwarf here. For the white dwarf, we have different kinds of white dwarfs. You have white dwarfs which are very magnetized, like that we call the polars, and others that are less magnetized. And of course, when it's magnetized, then it's more difficult to accrete on the surface of the white dwarf. So, which is why you have some accretion disk, which is truncated in the center, and you have only accretion on the poles where the magnetic field is less strong here, and so you can have some accretion on these objects. And this is a result of a tomography study where you can see the gas stream, the bright spot coming from the mass donor and accreted on the white dwarf, and you also see this truncated accretion disk. So this was the case. So this system are also what we call the cataclysmic variables hosting a white dwarf. For neutron stars, you have something which is nearly similar, except that the magnetic field is stronger. Also, the capacity of the neutron star is higher, so you have more energy involved. And so you see this scheme, which shows the complexity of the accretion up to the magnetospheric radius here, depending on the. So you have the distance here from in a logarithmic scale. And so you have also very different phenomena that are related to the nature, to the system of around this neutron star object that gives rise to very different bursts and interesting phenomenology of accreting matter. And the last one, of course, is for the black holes. In fact, the phenomenology is very similar for the neutron star and black holes, and the energy involved is very similar also because the capacity is very close. So here you have again the same drawing, a companion star. You see the shape due to Roche geometry, accretion stream, and the accretion disk. And here you see some of these objects hosting black holes with accretion disk, and these are all to the same scale. So you can see different scales for the stars, but also for the accretion disk. And one of the objects that is most interesting in this field is GRS 1915 plus 105, which has a very big accretion disk, which means that there is a very, very big reservoir of matter that is accreted onto the black hole. And also you can see that there is Cygnus 61, which is here with a blue star. And I will just show it afterwards. And GRS 1915 plus 105 also shows, as you see here, in radius, some compact jets that also shows some superluminal motions if you look at a larger scale. This is another example of another jet source, 1E1740, and close to the galactic center. And this, in fact, gave the name of microquasar because you see the similarity with the quasar 3C175, I think, Okay, so in this case, you have energy involved, which is higher than the SS433 because you have jets that are nearly at a velocity of 92, 94 C. So it's much higher energy involved. Okay, so we have two kinds of accreting binaries. We have the low mass XY binary, where, as I said earlier, the companion star fills the Roche lobe, and then you have the high mass XY binary, where the star doesn't fill the Roche lobe because the mass of the star here is much bigger than the mass of the compact object, so it doesn't fill the Roche lobe, but you have a strong stellar wind, which is accreted onto the compact object. So both systems are can be transient. The only difference is that here you have all the matter from the companion star, which is accreted. So this is much more efficient than here. So energy involved here in the X-ray luminosity is much higher than for these sources. But for these sources also we have transient phenomena, as I will describe later. So this is, we know nearly 250 long mass X-ray binary now in our galaxy. So as I said, companion star is has a low mass, so the later than it's less than nearly 1 solar mass. You accrete through Roche lobe filling. This for instance was the case for the first source detected SCO-X1 in the 60s. And so this is the case for the mainly for all the microquasar for the jet sources. And for the case of the high mass X-ray binary, you have different systems. First, I can say that there are systems that are very close to microquasar, which are called the Roche lobe overflow systems. In this case, the star, we can call them a beginning atmospheric Roche lobe overflow because you have the surface of the star which touches the Roche lobe here, and so you have some matter which is channeled here through the L1 and accreted. This is the case, for instance, of Cygnus X1. I will show just afterwards. You have also then for the most standard cases, these are the supergiant X-ray binary. So here you have supergiant star, which has very strong wind, and this is the wind which would be accreted onto the compact object. The last one is the case of the BE systems. For these cases, you have a very star. So BE star, so main sequence star, which is rotating very quickly, which creates a decretion disk, and it's every time that the compact object penetrates the decretion disk that you have an accretion of matter, and so an emission in the X-rays. So all these systems can be transient with different temporal activity. And for this system, we know nearly 167 in our galaxy. So this is Cygnus X1. So all the information is in French, but don't look at what is written. It's too small anyway. So just look at the image. So the black hole is here. You have the supergiant, which is here. So the supergiant is 20 to 30 solar masses. As I said earlier, it has the characteristics of a low mass X-ray binary because the star is nearly filling the Roche lobe. So you have matter funneled here, passing through L1 and creating an accretion disk. But at the same time, it's a supergiant star. So see, it's also ejecting a very strong stellar wind. And this stellar wind is accreted onto the black hole, which happens to be the most massive black hole in an accreting binary in our galaxy. So it's nearly 20 solar masses. In fact, so this is what you see when you are close to the source. But if you go further away, you also see that this source is ejecting matter and interacting, as we saw for SS433 on the interstellar medium. It creates a cavity and interacts on all the interstellar medium which is around it. Okay, and I will finish with this. This is the galactic distribution of all the accreting binaries that we know of now in our galaxy. So you see the low mass X-ray binary in red, which are nearly concentrated, mostly concentrated into the galactic center because they are made of old stars. So low mass stars, old stars, mainly in the galactic center. And you see in blue the dots of the high mass X-ray binary, which are made of more recent stars because they are massive stars, 20 to 40 solar masses, so they don't live for a long time. So they are mostly concentrated towards the tangential point of the spiral arms, where you have complex, where you have the stellar formation complexes in the galaxy. And this last slide was just to show you the different masses that we can determine in these systems. Because of the Kepler law, it's very easy to get the masses of each system. Well, easy, not always easy observationally, but when you have the observation to make it, it's the calculation is easy. So this is for containing neutron star and white dwarf, and then neutron star and neutron star. You see it's very close to 1.4 solar masses. Then you have neutron star X-ray binaries, for which some neutron stars have a higher mass, mostly in the case of the recycled pulsar, because they gain more matter during the evolution of these sources. And then you have the black hole binaries with masses which are much higher because they are black holes. And I think I have finished with this microquasar system. Thank you very much.